All right, hey everybody. So today we are going to be starting forces. So we're just finishing up our 1D and 2D kinematics, and we're moving on to another part of physics, which is called dynamics. And dynamics has to do particularly with how things move, and that ultimately boils down to forces and the study of forces. So in today's video, what we're going to talk about is a definition of what forces are, some examples of forces in nature, and how Newton's 3 laws of motion deal with forces, and that will ultimately lead us to being able to solve force and motion problems that are in the one dimension. So getting started here. The definition of force is actually a really simple one. All a force is it's a push or a pull. So some examples of these pushes or pulls would be an object's weight. So the amount of mass an object has as it interacts with the gravitational pull on Earth. Of the Earth. Tension on a rope is an example, how the weight of an object interacts with pulling on a rope. Friction is another great example of a force. If you rub your hands together and you feel the heat that generates, that heat is due to frictional interactions between your hands. Another example would be attractions between an electron and a proton. Those are all great examples of different kinds of forces we have in nature. Just to clarify something right off the bat, I think people can be confused with. Forces do not necessarily arise from contact, so you do not have to be in contact with another object to exert a force on it. Well, you probably do, but other things don't. So for instance, although you are not in contact with the Earth, if you were to go skydiving, you would still experience the gravitational pull of the Earth as you would be plummeting towards the Earth. You do not have to be in contact with the Earth to experience this gravitational acceleration. So here are the 4 fundamental forces in nature, and this isn't necessarily something that you're going to be tested over in the future, but it's just good information to kind of have in your back pocket. So the 4 fundamental forces in nature is gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. The one that's going to be of principal concern in general physics is gravity. Gravity is something ultimately that we can quantify, and we will later in the semester. But for now, all you need to know is that gravity is any attraction between two objects that both have mass. So technically, you are gravitationally attracted to everything around you that has mass. We are gravitationally attracted to the Earth first and foremost because it happens to be the most massive thing we are near to. Although gravity is the weakest of the 4 fundamental forces, it is the most dominant, so it's the one we see most in nature. Ironically, it is also the one that is most poorly understood by science. There's a lot of really cool research going on in really fancy physics labs all over the country and the world that are studying how gravity is transmitted across great distances. So I would encourage you to peruse that area of study should it interest you. The next is the electromagnetic force. The electromagnetic force is between 2 bodies that happen to have charge. And this is something that we'll deal with when we study circuits, kind of, in May. But what you need to know for now is that this is simply one of the fundamental forces in nature, and it has either an attractive quality to it, so as we know, things with opposite charges attract, and then things with the same charge tend to push each other away. They have a repulsive interaction. The third is the weak nuclear force. This is responsible for atomic decay, so we see how different atoms can decay over time into other atoms. We have different types of decay, and this is all due to the weak nuclear force. The last is the strong nuclear force. This is the strongest force in nature. This is ultimately what holds quarks together. Quarks are the subatomic particles that make up protons and neutrons inside atoms, and it is the strongest of the fundamental forces that we have in nature. So, in case you're ever in jeopardy, you are well prepared. Leading into a discussion of forces, obviously the guy that came up with all of this was our good friend Isaac Newton. He postulated that there were 3 laws that govern motion of all objects in the universe. The first being the law of inertia. The second one being the relationship between net force and an object's mass and acceleration. And then lastly, the law of equal and opposite interactions. So first, let's talk about the first law, the law of inertia. It's commonly stated as being thus: an object in motion tends to stay in motion, and an object at rest tends to stay at rest. Well, that seems pretty simple. basically all you can say is that an object that's moving will stay moving with the same velocity, meaning the same speed and the same direction, until some sort of force outside of itself acts on it. If an object is at rest, it will continue to stay at rest until there is an external force that acts on this object. So basically, all this is saying is that it takes force to change an object's velocity. So, we're going to quantify what this means when we get to the second law, but for now, think about this. If you have a pen sitting on your desk, it will stay sitting on your desk until there's a force put in to change the equilibrium of forces acting on your pen. As the pen sits on the table in front of you, or your iPad, whatever you have in front of you, put it on a table, you'll notice that obviously the iPad is pulled into the table. But conversely, something we can't necessarily experience is that the table is pushing back on the iPad. We'll talk about this when we get to the third law. But it takes either a push up or a push down, or perhaps a push to the side, to make an object change its resting position. So this is something that perhaps isn't what we experience in nature. For instance, if you were to give a pen a shove across the desk, it wouldn't continue to go forever. And we'll talk about why that is a little bit later, but suffice it to say, it takes outside interactions of forces to bring objects out of their state of motion. So for instance, for an example, an astronaut is in outer space, and like this person here, and if they were in outer space and given perhaps a push or a pull, they would continue moving in the same direction with the same speed forever until something else would change that. So for instance, if you gave this astronaut person a shove this way, they would continue moving in this direction with however much speed they had at the moment of your shove forever and for all eternity. Now, this is something we don't always experience here on Earth. Like we said earlier, things tend to slow when we push them. This is because we have outside forces interacting, and we call these outside forces friction. But when you're in space, there's no friction all around you. There's no air in space. There's no contact pressure due to other outside forces. So if you were to give a person a shove in space, they would go for forever. His second law is actually a mathematical equation, this one right here. The net force is equal to an object's mass times its acceleration. What this equation serves to do is to show us how an object with mass can accelerate given a certain amount of force inputted into the system. So, this is like any other equation that we've seen thus far, any of our kinematics equations. You can see it's all on the same line, so it's a lovely linear formula, and we'll see a graph of it a little bit later on. But what you can say is that the acceleration an object undergoes is directly proportional to the net force acting on it. So if we were to isolate any of these quantities, if we wanted to isolate acceleration, for instance, we divide by m on this side and divide by m on this side. So we could say that acceleration is equal to f over m. So the greater the acceleration, the greater the force. These two terms are tied completely together. If you increase an object's force, or you increase the amount of force acting on an object, you would therefore increase the acceleration that object experiences. And this is something that makes sense. We've experienced this, right? The harder you push on something, the faster it tends to go. So if you're playing football, for instance, and you're running with someone, the harder you shove someone, the further they will go away from you, the faster their acceleration. Or perhaps the harder you hit a tennis ball, the more force you put into it, the more quickly that object will accelerate to your opponent. Now, that being said, the other proportion that we haven't talked about yet is that of mass. Now remember, all mass is the amount of stuff that's in an object. So, for instance, if we were to talk about a tennis ball compared to that of a moving truck, a tennis ball has much less mass than a moving truck does. A moving truck is a much more massive object. There's a lot more stuff in that. Now, the more mass an object has, the more force it takes to accelerate it. It takes a lot more push or pull to move a moving truck than it does to move a tennis ball. So again, the more massive that object is, the more force it takes to manipulate that object. It's important to note that force is in fact a vector. It has a magnitude and it has a direction. That will come into play here in about 3 minutes when we talk about different equations and different problems that we do utilizing these forces. And this is kind of a cool caveat like we've talked about just a minute ago. When we talk about Newton's first law, it's really a special case of Newton's second law. So when we talk about an object remaining in its state, so be that in motion or be that at rest, what we're really saying is net force is zero. There's no net force acting on this object. Therefore, it will continue to move. Its mass will move at the same acceleration, which is zero. There's no acceleration if an object's velocity is constant. Okay, so what does it mean to have net force? What is this net force quantity, this F net right here? Sometimes you'll also see this written as a capital sigma F. Net force is when there's more than one force acting on a body. And when there's more than one force, like we talked about with our vector operations, we can add those vectors together to find a resultant force, or the combination of all of those forces put together, the addition of all of those forces. So as you can see in this example here, you have force 1, which is going this way, and remember the length of the vector refers to its magnitude. So this is by far the largest magnitude vector. There's this vector here, which is in probably a little bit less magnitude, but obviously pointing in a very different direction. And this one, which has the least magnitude and pointing again in an opposite direction. If we were to add all of these different vectors together, pointing in all of their different ways, we would ultimately come out with this vector here. This is your net or your resultant vector. The combination of all of your forces put together here is really the same thing as saying this vector here. So we can summarize or shorthand all of these different vectors together to be equal to just this vector. And we'll practice doing that a little bit later. So here's an example of putting net force into Newton's second law, putting all of these things into action. We have a little situation here where we have an object which has a 2 kilogram mass, which is this little guy right here. It's experiencing 3 forces. This red vector here, a 15 Newton force to the left. This black vector here, a 32 Newton force to the right, as well as a 10 Newton green force to the right. We can combine all of these together. And remember, we use the standard Cartesian grid here in physics, where we say to the right is positive and to the left is negative. Because we're on the same plane, these are both on the x-axis, just like we did in vector operations, we can add all of these together. So we would do 32 plus 10, so that would be the same as saying there is a 42 Newton force to the right, but we would subtract away 15 newtons to the left, and ultimately that comes to a net force of 27 newtons to the right. So the net force acting on this object is 27 newtons. Now we would want to find perhaps this object's acceleration. Given that we have all of these forces acting upon this object, what is this object's acceleration? So using Newton's second law, net force is equal to mass times acceleration. We know our net force is 27 newtons to the right. We know our mass is 2 kilograms. Solving for that, we would come to 13.5 meters per second squared. And that acceleration would also be to the right. Your net force and your acceleration will always be in the same direction. So there you go. You've done a Newton's second law problem. So in terms of just a quick chat about units, force is always given in units called newtons. Again, it's a good gig if you can become a scientist and discover something amazing like Newton's 3 laws, because then you can name things after yourself. So the units for force are newtons, and we abbreviate that in physics, which is a capital N. So anytime you see a force rating, it will always be in newtons, and newtons are vector quantities. A newton is the same thing, so if we were to look at this N and like what the heck does just N mean, 1 newton is the same thing as saying 1 kilogram moving at 1 meters per second squared. So whenever you're doing your problems and you're running into some unit confusion perhaps when you try and simplify things down, a newton is the same as 1 kilogram meters per second squared. And again, newton is a force measurement. It's not a mass measurement. Remember, that's kilograms. And then acceleration is still in meters per second squared. The conversion between pounds and newtons is given right here. So 1 pound that we use here in the United States is the same thing as about 4.45 newtons. So a quick chat about graphing these things. So remember how we talked about force and acceleration as being two quantities that have a linear relationship? They are directly proportional. So if we were to plot force versus acceleration, we would get a really lovely linear slope here. So again, acceleration being your quantity here that is dependent upon force. And you see how we can get a really lovely linear slope here. So what this would be saying is that, again, we've done this before when we did our kinematics graphs. But if we have rise over run, so change in force over the change of acceleration, the slope is going to be equal to the object's mass. So delta F over delta A is equal to m. So again, all of this will be dependent upon the object's mass. So the greater the force that is put in, the greater the acceleration given a constant mass. So if you were to plot force data versus acceleration data over different increments of force and then given acceleration, you would be able to calculate an unknown for mass, which sounds like an awesome lab. Keep that in the back of your head. A quick discussion about weight. This is something that is confusing in physics and how we use the terms in just everyday society. But weight is equal to the object's mass times its acceleration due to gravity, which we know here on Earth is 9.8 meters per second squared. Weight is not the same thing as mass. Remember, weight is going to be given in units of newtons in the SI system because weight is a force. Mass, again, is just how much stuff is in an object. So if you're given an object's mass, perhaps 2 kilograms, in order to find its weight, you would need to, assuming we're on Earth, multiply it by 9.8 meters per second squared. So again, mass is acceleration due to gravity of whatever gravity you're experiencing, and again, most of the times we're going to be on Earth, so that's just going to be 9.8. So look how this equation here, weight is equal to mass times gravity, is simply a derivation of F equals ma. It's simply a derivation of Newton's second law. Keep that in mind. The last of Newton's laws is the third law, which is the law of action and reaction. Usually you hear little third graders say it. For every action there is an equal but opposite reaction. And I think this can sometimes be, while it's very simple to say, somewhat counterintuitive. The idea would be that every time you have two things that are interacting with each other, they are pushing and pulling on each other in the same amount. So, for instance, the example I have up here, if you hit a tennis ball with a racket, the force on the ball due to the racket is the exact same force experienced by the racket due to the ball, except they're going to be going in opposing directions. Again, so if you drop an apple towards the earth is pulling on the apple just as hard as the apple pulls on the earth. So as an apple falls towards earth, just as earth is pulling the apple down, the apple is pulling the earth up. The last example of Newton's third law, if you're to fire a rifle, the bullet will be pushing the rifle backwards, just as hard as the rifle pushes the bullet forward. So you see that, and I think this is a good example because you can see when someone fires a gun, you see that there's that recoil. The recoil is due to the fact that the gun is pushing back. The bullet, rather, is pushing back on the gun, just as the gun is pushing the bullet forwards. Now again, we see two very different accelerations, the bullet obviously moving at a much greater acceleration than the rifle, and again, that is simply due to differences in mass. So here's the example, quantified, of Newton's third law. So again, we had the example of the apple falling towards the earth, but then the earth falling up to meet the apple. And remember how I said all this is a difference in masses? Well, here it is quantified for you. So again, we have a 0.4 kilogram apple, that's its mass, but it has a weight of 3.92 newtons. Now remember, I was able to get that weight using the equation weight is equal to mass times gravitational acceleration, which on Earth is 9.8. So I took 0.4 right here, multiplied it by 9.8 to come out with a 3.92 Newton weight. The apple's weight is the Earth's force on this apple. Now, the apple is going to pull back just as hard as the Earth pulls on it. Now, again, the Earth is going to be, so the apple is pulled down 3.92 newtons worth of force for weight. It's pulling up its same weight on the Earth. But if you look at the Earth's mass, it's a very, very large number. Therefore, the acceleration you would get by taking your mass right here and dividing your weight by your mass to get your acceleration, it's going to be a much smaller number, a very, very small number. So anytime you have, this is actually a positive thing, right? You don't want the apple's motion to disrupt the motion of the Earth. That would make life on Earth very challenging. So we are appreciative of the Earth's massive size. Therefore, dropping things doesn't change the course of our existence. Yay! Okay, so here's a picture to quantify what I'm speaking of. So again, they're equal and opposite forces. Remember, force is equal to ma, so we have ma here, ma here. Again, the apple has a very small mass, so it has a massive acceleration. The Earth has a massive mass, and therefore has a very little acceleration. These two quantities are going to be tied because, again, the forces are the same. F equals ma here, F equals ma here. They're set equal to one another because, again, the forces are the same. Okay, so just to quickly recap, here are the things that we talked about today. We firstly defined what a force was. We talked about the 4 fundamental forces that we find in nature, and then we went through Newton's 3 laws, the laws of inertia, the laws of interaction, and the laws of net force equaling mass times acceleration. We also went over how to do some quick force problems in 1 dimension. Next time we'll be talking about different types of forces as well as different types of frictional interactions. Until then, see you later.